Welcome back. Let's talk about encryption. Substitution ciphers, frequency analysis, polyalphabetic ciphers, and so forth. And we'll round up with some standard forms of encryption that are used today. So first of all, some terminology, some areas that might be a little bit confusing. So an encryption or a cipher can be thought of as a reversible hash function. So in the previous section, we talked about functions and hashes. And mathematically speaking, a function is reversible and a hash is not. But in an encryption, sometimes the word hash is used because they're referring to the idea that the data is all mixed up. But keep in mind, in order for encryption to work, it needs to be reversible. Otherwise, you can't decode. So be careful there. The term hash has a slightly different meaning in encryption sometimes. All right, so some more terminology. We have the term text, or sometimes just called the data or the plain text. And then we encrypt that, and that's the output, which is sometimes called a cipher or e-text for encrypted text or ciphertext. So there's two required components to do encryption. There's the algorithm, and then there's the key. Okay, and one or both of these can be kept secret. Like, you can just keep this key secret and let everybody know the algorithm, or you could do the other way around, although that's inconvenient. And if you really want to be secret, you could keep both of these secret. And that's what the military does. They'll actually keep the algorithm secret, and they'll have two boxes, two computers with the algorithm in it, and they'll fly one out there in a big jet and, plop it down. So the algorithm is secret, okay? This is impractical in real life, and typically when you're on the internet doing stuff, the algorithms are public. Everybody knows that, and then the key is the piece of private data. All right, but in theory, you could keep both secret if you really wanted to be secure. Okay, the simplest form of cipher is a substitution cipher, where you just replace one piece of data for another. So we're gonna deal with characters because the theory is easier to understand using characters, but the data could be other things besides characters. So the simplest kind of cipher is a Caesar cipher, presumably named after the Emperor Caesar, or either that or it's the guy from the pizza guy from Little Caesars. It's probably not, but anyway. So here's a simple Caesar cipher with a key of 3. So in a Caesar cipher, the algorithm is shift the letters by the key. That's the algorithm. Shift the letter by the key. So you have the alphabet here, A through Z, and you just scoot the whole thing down by, in this case, assume the key were 3. You just move the whole thing down by 3. So 1, 2, 3 is D. So you just scoot everything down. D comes over here, and then the rest of the alphabet, and you get to Z, and then you roll over to A, B, C. So that's a Caesar cipher. In the end, it's just a substitution. You're just mapping A into B, or to D rather, and B into E, and C into F. So it's a function. It's robust and deterministic. It's one-to-one and it's onto, therefore it's reversible. Okay, so we can encrypt from C to F, and then we can decrypt back from F to C. So for example, the plain text Dan would encrypt to G to Q, because D would be G, and A would be D, and N would be Q. All right, so the key space. So how many possible keys are there with this algorithm? Well, there's 25, right? You can shift between 1 and 25 times. If you shift 26 times, you're back to the original mapping. So there's 25 possible keys for this algorithm. So it's not a very secure algorithm because you could guess the key. You could in a computer, you could just try all 25 keys. It won't take you very long to do that, and one of those keys will produce the original output. So pretty easy to crack. Okay, but that's a substitution cipher. Here's another form of substitution cipher with a slightly different algorithm, but you could use the same kind of key. So here we have every nth letter cipher, where we generate a mapping by picking every nth letter out of the original sequence. So if we're picking every third letter, we'd go A, and then 1, 2, 3 would be D. Okay, so D comes over here, and then 1, 2, 3 would be G, and then 1, 2, 3 would be J, like that. So you generate you generate an output mapping by just picking every third letter. It's still just a straight out substitution. So to encrypt, D, you would just pick the J out of the table here. Likewise, there's only 25 possible keys, because if you pick every 26th letter, you're picking the same letter over again. So the key space, or the number of possible keys, is 25. You could still just guess the key. But the point here is that both of these, Caesar cipher and every nth letter cipher, they're both substitution ciphers. We're just substituting every input letter for an output letter. Okay, and there's other algorithms that you could imagine that are more complicated. That like you could pick you could pick 2 letters and then 1 letter and then 3 letters and 1 letter, or whatever. You could generate some other fancy way to pick these, but in the end, you end up with just a 1-to-1 mapping with a key space of 25. Okay. All right. So because of that, all of these substitution ciphers are vulnerable to, well, not only to guessing the keys, but you could also do what's called a frequency analysis. So if you know something about the original data, like let's say you happen to know that it's English, for example, there are patterns in English. That is, in the letters in the English language, there's frequency distributions. Like E is the most common language most common letter in the English language. 12.3% of the letters in English are E's. And then T is the next most common. 8.37% of the letters in the English language are T's. And S is another common letter. Okay, so if you know that what you're trying to decrypt or crack is English, you can apply this. I like to call this the Wheel of Fortune rule. Right? If you're buying a vowel in Wheel of Fortune, the game show Wheel of Fortune, it's good to buy an E, because chances are there will be one. That is, if you're clueless on what there could be and you're just randomly guessing. Or if you wanted to guess a consonant, you could guess T, because there's a lot of T's. Once again, that's if you're only clueless. If you happen to have some other clues, then there might be other things that you might want to guess. Okay, so there's frequency distributions in English. Now you can hide those by doing what's called a polyalphabetic substitution cipher. So it's always, it goes like this. There's an arms race going on with encryption, right? You come up with an encryption methodology like Caesar. Caesar came up with this thing, and then people would crack it. You analyze the weaknesses, you crack it. So then you come up with another algorithm, nth letter, and then people crack it, and then you come up with another thing. So a polyalphabetic substitution cipher is designed to hide these frequency patterns. Here's an example. Let's say you wanted to code up elephant. You could code elephant into this ciphertext 1, 2, 3, 4 if you do this mapping right here. If you just take every 2 letters, so EL would map to 1, and EP would map to 2, HA would map to 3, and NT would map to 4. I'm just trying to explain the idea of every 2 letter pairs maps to some number, and I'm using 1, 2, 3, 4 because it's convenient. Really, you'd start with AA, and that would be 1, and then AB would be 2, and then AC would be 3, like that, all the way to ZZ. And what would ZZ be? So there's this many mappings. So we're really writing a 2-digit base 26 letter, a 2-digit base 26, number or string, if you want. So there's 26 squared, or 767. So this is, this would, 1 to 676 would be ZZ. But I'm just using 1, 2, 3, 4 for convenience. So if there's 676 patterns, there's 676 2-letter combinations. So I need to be able to represent a value up to 676. So I need at least 10 bits, because 2 to the 9th would be 512. It's not big enough. So I need 10 bits. So it might look like this, using a 10-bit representation. EL is 1, and EP is 2, and HA is 3, like that. Okay, so this effectively hides the occurrence of E, because E is paired with another letter always. Okay, it hides the frequency of E. So you can't do a monoalphabetic frequency analysis. But you can still do a frequency analysis. You just have to go by pairs. But that requires a lot more data. So whereas you could break a monoalphabetic cipher, this kind of thing, like the Wheel of Fortune game, you could break this with a couple hundred words. You could break this. But to crack a polyalphabetic cipher, you'd need many more. You need a whole book. You'd need a lot more letters, but there'd still be patterns in the data, is the point. For example, the frequency of IT, the word it, TH shows up more often. ES. There's certain pairs in English that show up more frequent than others. All right, so that's substitution ciphers, and the fact that you can crack substitution ciphers with frequency analysis, and also by guessing the key. Here's a whole nother kind of way to do ciphers. You can do a transposition or a permutation cipher. So a permutation cipher uses the same original data, it just mixes it up. And that's where the term hash comes from. This rearranging the data. Sometimes they refer to that as a kind of hash. So here, for example, I could take peanut butter, and I could just mix up the letters and get this. So it's like an anagram, although this isn't a word, but anagrams typically form other words. And here you're just mixing up the letters, the same letters, right? There's a P somewhere, there's an E, there's two E's, there's a couple of A's. Okay, same letters, but just mixed up. So one way to do that is use a matrix. So you can consider this matrix to be the algorithm. And the algorithm is you write in the plain text data down the column. So I like peanut butter and jelly. And then you read it out across the rows. So it's IEUNY. Okay, like that. So you write it down and then read it across. And the key could be the key. So there's two things, right? There's the algorithm and then there's the key. You could consider the algorithm to be write down, read across. And then the key would be something like the table dimensions, like 5 by 5 would be the key. So same algorithm, write down, read across, but you could use a different size table. So that would be the key data that you would keep secret. Okay, just generally speaking, you could do more complicated permutations than this, but there's the rules that you use to do the permutation, and then there's the size of the if you're using a matrix, to be the size of the matrix. But there's an algorithm and then there's a key, generally speaking. Okay, so limitations of both of these things. Let's put on our bad guy hat now and be the bad guy for a little bit. How can we crack some of this stuff? Well, in the end, there's going to be patterns. Unless you really mix it up really good, there's going to be patterns. So a good cipher tries to hide these patterns. That is, it mixes up the data as much as possible to make the data appear as random as possible. That's a good cipher. And the other thing you want is a big key space. You don't just want 25 as the possible keys. You want, a lot of keys, zillions of keys. So that's the key space consideration. So a good cipher has a big key space. Like, for example, what's called 128-bit key encryption nowadays is referring to the key size. There's 2 to the 128 possible keys. and punch that into your calculator, 2 to the 128. It's huge. There's more numbers. If you were just sitting down with your computer and, you know, had it guessing every possible key, it would take till the end of the universe before you could guess this many keys. So guessing the keys is impractical, even with, you know, huge arrays of machines. It's a little bit like Bitcoin mining. That's a different thing, but Bitcoin mining is a good analogy of an extremely complicated or extremely time-intensive computation. It just doesn't pay off, and, you know, for most people. Anyway, okay, let's look at another form of encryption here. So I've titled this private key encryption. Previously we were really talking about that, like substitution ciphers with the key of 3. You know, the key could be kept private. The three could be kept private. That's what we mean by private key encryption. But here's another form of encryption using the XOR operator. So here's the definition of XOR. If you have 2 inputs, these are all the possible combinations of inputs, and this is what XOR would give you. So 0, 0 gives you 0, and 0, 1 gives you 1. All of these. So basically, XOR produces a 1 if the 2 inputs are different than each other, right? So on this row and this row, it produces a 1 because the 2 inputs are different. So it has this interesting property that if you take the plain text T and apply the key to it, you'll get this encrypted data, E. And it's reversible simply by taking the encrypted data, E, and applying the key to it again. So you can go from encrypted to plain text, and then you can go from plain text to encrypted and then back to plain text just by applying the key twice. Here's an example. So here I have a plain text bit pattern, which could be a byte, you know, but you could do this at 64 bits at a time, and you're just doing an XOR, which is a very fast operation in the computer. It's a binary operation. It's very quick. That's why we like this. But just doing it on a byte here, so I have a key I made up here, just 01010101 is the key, and then the data, plain text data, is 11001100. And if you do the XOR on this, you get this. So we're just generating ones where the 2 bits are different here. So here the bit's different, and here the 2 bits are different, and here the 2 bits are different, and here. Okay, so we get this E. Put the E down here and apply the key again, and you're back to the plain text. So a very quick 1 clock cycle XOR operation will encrypt, and then another, you know, very quick 1 clock cycle XOR operation will decrypt. So XOR has that characteristic, which leads us to what's done now. Well, for a long time there was something called data encryption standard and triple data encryption standard. They've moved beyond that now, but the theory is the same. Okay, so this is a good thing academically to study because it's small enough that we can wrap our heads around, and the theory is the same. So we've talked about substitution, right, where you just swap out letters, or you swap out chunks of data for another chunk of data. And then we talked about permutation, where you take the data and just mix it up. Okay, and then we looked at XOR, where you just apply XOR to a set of data and then reverse that. So 3DS, DES, Data Encryption Standard, just does that. And it does a permutation, a substitution, and an XOR. So what it does, it takes 64 bits, and here it is. Right here. It takes 64-bit bits, and it cuts that in half into two 32-bit chunks. And the old right chunk becomes the new left chunk for the next cycle. Basically, right here, you take the input, and it does an initial permutation on it. That's not in here. It should be, but it takes the 64 bits and breaks it in half. That's what's going on here. And this old right chunk goes over here. Basically, this right chunk becomes the new left chunk for the next cycle right there. And then we just do a substitution and a permutation on this chunk. So we do a substitution which is kind of like a Caesar cipher, but more fancy than that. But it's a substitution. We substitute each chunk of data for another chunk of data. Then we take those pieces of data and mix them all up. We do a permutation on that. Then we take this left chunk right here and we do an XOR. This is an XOR right here. That gives us this. Okay, and then the original right chunk, which came over here, we're now at this point, and we just repeat that. We just on the right chunk, we do a substitution, permutation, XOR, and we end up with this guy. And then we take this right guy over here and XOR him with this result. And then, so we do this 16 times. That's data encryption standard. At the end, you combine the two chunks and do one more substitution. No, you do one more permutation, and then you get the output. Okay, so simply stated, or at the most basic level, you're doing a substitution driven by the key, then you're doing a permutation, then you're doing an XOR, and then you're doing that 16 times. Okay, so substitution, permutation, XOR, over and over again. So I'd like you to do this. So I've got this mini 8-bit implementation that we can implement. So let's walk through this here. We've got, we're going to do 8 bits at a time. So we'll take an 8-bit chunk of data called W0. We'll do a substitution, we'll do a transposition, and then we'll do an XOR. And we get an output chunk of data, another byte. So a byte in, substitution, transposition, XOR, and we get a byte. Then we do that 4 more or 3 more times. Okay, so we're doing this block here 4 times. And in more detail, the substitution is described here, the transposition is described here, and the XOR is described here. So we've got an 8-bit key. There's 8-bit data value and an 8-bit key. The key could be expressed as a base 4 number. So, for example, let's say the key were that's 8 bits. Let's say this were the key. You could break this up like that. So these have the values 0, 1, 2, 3. It's a base 4 number, right? Because if it were base 4, you'd have 4 to the 0, 4 to the 1, 4 squared, 4 to the third, or 1, 4, 16. Is this 256? I'm not sure. I think so. And yeah, this is 64. Anyway, you could look at this as a base 4 number if you group these bits in 2s, but really all we need is these indexes right here, to do this mapping. That's all we need. If you're curious, you could just if we just did binary to decimal, just while we're playing around with this, we could, you know, so 00011011 is going to be no, it's going to be 27. But you could also go base 4 to decimal, which would be so this is the 64s, the 16s, the 4s, and the 1s. So there's 1 16 plus 2 4s plus 3 1s, which is 16 plus 8 plus 3, which is 27. So, I mean, you can take an 8-bit binary number and you can express it as a 4-digit base 4 number. You can do that, but really what we need is these 4 indexes. I want to be able to use a 8-bit key, and from that I want to extract 4 indexes. This is all I really want, and that's what I'm trying to say here. I'm just trying to say you can group the bits in the 8-bit number into pairs of 2, and then you can use those as indexes into a table for the substitution. Okay, so look here for the substitution. I'm trying a lookup from a table based on S for this first table, and S is the first 2 bits of this is S. QS QR is it SRQP or PQRS really. So I'm using S as the index into this table here, and I'm using R, and I'm using Q, and I'm using P. So basically I'm using, if this were the key value, then I'd be using 0 here, and I'd be using 1 here, and I'd be using 2 here, and I'd be using 3 here. So I'm looking up in a 2-dimensional table where the first, so rows, comma, column, so the column is W0, and the row is given by S. So it's just extracting a byte from a lookup table driven by the key, or driven by 2 bits of the key. And then here I'm doing another substitution driven by the next 2 bits of the key. Then here I'm doing another substitution driven by these 2 bits of the key. And here I'm driving a substitution by these other 2 bits. So I can have a key-driven substitution. So you're going to feed an input data into here, and then you're going to feed a key into this whole algorithm, and the key will get busted up into SQ, R, and P, and those SQRP values are going to drive the lookups. We'll have to look at the code in a bit, which is kind of what's happening now. We're going to transition into the code. So anyway, you do a transition, or you do a substitution driven by the key, where I break the key up into 2-bit fields, and I use that to drive the substitution. Then I'm going to do a transposition on the data. I'm just going to mix up the data, and the easiest thing to do is swap the nibbles. So I'm just gonna take the 4 bits and swap them. So this is the low order bit concatenated with the high order bit. Right, low order bit concatenated with the high order bit. So I'm just swapping, you know, I'm swapping x sub high with x sub low. That's the transposition. Right, so you take a byte in, substitute it for another byte, swap the nibbles. That's the transposition. XOR that with the key. Just doing, you know, 8-bit XOR with the key. That's the first stage. Then we do this 3 more times, with different lookups on the lookup tables. Okay, I'll have to make another video where we go through this in a little bit more detail. But that's the basic idea. The last thing we want to talk about here is this idea of public key encryption, which you should be introduced to at some point if you haven't already. So there's two general categories of encryption in modern systems. There's what's called private key encryption, and then there's public key encryption. So private key encryption is pretty much what we've been talking about in this lecture, where you have an algorithm and then you have a key. And typically the algorithm is public. That is, it's software that's installed on every machine. And then the key is private. Okay, so you have two computers that are trying to communicate. All they need to do is keep this key secret. Now that's a nice algorithm because it's computationally efficient. It's fast. That is, this thing we just went through a minute ago, that flowchart is pretty fast when it runs. So we like that. The problem is, how do you get a private key to another computer over a public network? Right? The internet is a public network. It's, you know, your communications are traveling through any number of servers which anybody could spy on at any time. You could climb a telephone pole and spy on people's communications. So how do you get this private key over to another computer? Well, there's this amazing thing called public key encryption that was invented coincidentally right before it was needed in a big way by supposedly two independent research teams, which is also incredibly unlikely. So anyway, you know, this stuff was funded at universities, you know, by the government for their secret stuff. And then all of a sudden, you know, these two teams, hey, we just invented this thing and it has enormous market potential. But, you know, make of that what you will. But anyway, public key encryption, I don't want to go into the details of how it works. It involves prime number factoring and some other magical stuff. But what it's basically used for is to transmit these private keys. Okay, so it's computationally inefficient. You know, like doing the calculations that are involved in this transmission is slow, but you only need to do it enough to get this private key over to the other computer. And then once you've done that, then you can proceed with the DES kind of thing that we just talked about. Right, so this is way beyond the scope of the course, but you should be aware of it. There are these two things, and this is worth some further study if you get the opportunity. All right, that pretty much wraps up the encryption stuff. I hope that was useful to you, and great. We'll see you next time. Thanks. Bye-bye.